March 17, 1945. Somewhere over the Ruhr Valley, Germany. Lieutenant James Caldwell's hands gripped the control stick of his P-47 Thunderbolt as the morning mist began to burn away from the railway lines below. He had flown 43 missions over occupied Europe, strafed countless convoys, and engaged enemy fighters more times than he cared to remember. But what he was about to attempt in the next 15 minutes would rewrite the tactical manual for ground attack aviation and expose a vulnerability in German logistics that High Command had dismissed as impossible. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. The intelligence briefing 3 days earlier had been explicit. Do not engage armored trains. Do not attempt to strafe reinforced rail infrastructure. The 850 caliber machine guns mounted in his aircraft's wings were formidable against soft targets, but German engineers had spent 4 years hardening their supply routes against exactly this kind of attack. What the brass hadn't counted on was American ingenuity, pilot desperation, and the devastating power of concentrated firepower applied to precisely calculated weak points. The story I'm about to share reveals how a discovery made during a moment of split-second decision-making transformed the air war over Europe and cost Germany resources it could never replace. Most people assume that strategic bombing won the air war over Europe through the systematic destruction of factories, oil refineries, and military installations. The truth is far more complex and far more immediate. While heavy bombers attacked industrial targets that took months to rebuild, fighter bombers discovered they could sever the arteries connecting those factories to the front lines in minutes. The difference between strategic and tactical impact became measured not in tonnage of bombs dropped, but in tons of supplies that never reached German divisions bleeding out in defensive positions across France and the Low Countries. By spring of 1945, the Luftwaffe had been effectively neutralized as a strategic threat. American and British fighters dominated the skies to such an extent that German aircraft rarely challenged daylight operations. This air supremacy created an unexpected problem for Allied fighter pilots. With fewer aerial targets to engage, hundreds of highly trained combat aviators found themselves relegated to ground attack missions that felt less like aerial combat and more like airborne artillery. Lieutenant James Caldwell belonged to the 362nd Fighter Squadron, part of the 9th Air Force's Tactical Aviation Command. His unit operated from a forward airfield designated as 78, a hastily constructed facility near Florence, Belgium that consisted of pierced steel planking laid across flattened farmland. The base had been operational for less than 6 weeks, carved out of liberated territory as Allied armies pushed deeper into Germany. The living conditions reflected the temporary nature of these forward positions. Pilots slept in tents heated by salvaged German stoves. Mess facilities served rations supplemented by whatever local supplies could be procured. Briefing rooms were converted cargo containers where intelligence officers used hand-drawn maps because printed materials couldn't keep pace with the rapidly shifting front lines. But the aircraft received meticulous maintenance despite primitive conditions. Ground crews worked through Belgian winter nights to keep every P-47 mission capable, understanding that their efforts directly impacted pilot survival and mission success. James had joined the Army Air Forces in 1942, immediately after graduating from a small college in upstate New York where he had studied mechanical engineering. His technical background made him valuable during training, where he quickly grasped the relationships between aircraft systems, flight dynamics, and combat tactics. Instructors noted his ability to calculate deflection angles, fuel consumption rates, and ammunition expenditure with unusual precision. These skills translated directly to combat effectiveness once he reached operational squadrons. His first combat mission had been flown over France in August 1944, providing close air support for ground forces breaking out from the Normandy beachhead. The experience had been overwhelming. Anti-aircraft fire creating black bursts across the sky, radio channels saturated with urgent calls for assistance, and the surreal experience of watching his tracer rounds impact enemy positions while friendly troops waved from foxholes barely 100 yards away. He had returned from that mission physically unharmed but mentally exhausted, understanding for the first time the difference between training scenarios and actual combat where mistakes killed people. 42 missions later, James had developed the kind of operational instincts that separated experienced pilots from those still learning through trial and error. He could read terrain features to predict likely enemy positions. He understood how to use altitude, speed, and sun position to minimize exposure to ground fire. He knew which targets justified the risk of multiple attack runs and which required a single pass followed by immediate departure from the target area. The mission briefing on March 14 had introduced a target set that generated considerable discussion among the assembled pilots. Intelligence had identified increased rail traffic moving through the Ruhr Valley, suggesting German forces were attempting to reposition reserves or evacuate equipment ahead of advancing Allied armies. Aerial reconnaissance had documented dozens of trains moving primarily during twilight hours when low light conditions reduced vulnerability to air attack. The challenge was that these weren't ordinary freight trains carrying supplies in open cars. These were armored military trains specifically designed to survive air attack. Captain Robert Mitchell, the squadron intelligence officer, had displayed reconnaissance photographs showing the construction of these formidable targets. The locomotives were protected by sloped armor plates that deflected small arms fire and shell fragments. Flat cars carried anti-aircraft guns manned by dedicated crews trained specifically for railway defense. Additional cars housed infantry squads ready to disembark and defend trains that were forced to stop. The entire configuration represented a mobile fortress that could fight back effectively against air attack. Previous attempts to destroy these trains had produced disappointing results. Heavy bombers flying at altitude rarely achieved direct hits on moving targets. Medium bombers attacking from lower altitudes faced concentrated anti-aircraft fire from both the trains and surrounding defensive positions. Fighter bombers conducting strafing runs found their machine gun fire ineffective against armored components, typically succeeding only in killing exposed personnel or damaging unprotected sections. Captain Mitchell's assessment was blunt. Armored trains were designated as targets of opportunity only. If pilots encountered them during other missions and conditions were favorable, they could engage. But dedicated missions against these targets were not authorized due to unfavorable risk-to-reward ratios. The armor was too effective, the defensive firepower too concentrated, and the probability of mission kill too low to justify the aircraft and pilot losses that would result from sustained attacks. James had listened to this briefing with growing frustration. His engineering background made him skeptical of the conclusion that these trains were essentially invulnerable to fighter attack. Armor was effective against certain types of damage but had inherent weaknesses at joints, transitions, and points where different materials met. The 50 caliber rounds fired by his aircraft's 8 machine guns possessed tremendous kinetic energy. Individually, each round might not penetrate heavy armor. But concentrated fire from multiple guns converging on a single point might achieve results that dispersed fire could not. After the briefing, he had approached Captain Mitchell with questions about the specific armor configurations protecting the locomotives. The intelligence officer had pulled additional reconnaissance photos showing detailed views of several captured or destroyed German rail engines. The armor consisted of plates bolted to the locomotive's frame, creating a protective shell around vital components. But the attachment points, the seams between plates, and the necessary openings for mechanical linkages represented potential vulnerabilities. James spent that evening in his tent sketching diagrams and performing calculations. The P-47 Thunderbolt carried 8 M2 Browning machine guns, 4 mounted in each wing. Each gun fired at approximately 800 rounds per minute, meaning the combined battery could deliver over 6,000 rounds per minute when all guns fired simultaneously. The pilot controlled this firepower through a single trigger, with all 8 guns harmonized to converge at a specific range, typically set between 250 and 300 yards. The kinetic energy delivered by this concentration of fire was substantial. Each 50 caliber round possessed significant armor-penetrating capability against light to medium protection. While individual rounds might not breach heavy armor, the cumulative effect of dozens of rounds impacting within seconds at a single point might overwhelm even robust protection through sheer mechanical stress. Metal fatigues under repeated impacts. Welds crack. Bolts shear. Armor that could stop any individual round might fail catastrophically when subjected to sustained concentrated fire. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The question was where to aim. Locomotives presented large targets, but most of their bulk was protected by armor or contained non-critical components. Destroying a train required more than cosmetic damage. It required hitting something that would cause immediate catastrophic failure, rendering the train immobile or forcing its abandonment. James studied the mechanical drawings of German locomotives that intelligence had compiled from various sources. The critical vulnerability became apparent after several hours of analysis. The coupling mechanisms connecting locomotives to their trains represented a confluence of mechanical stresses, vulnerable materials, and essential functionality. These heavy-duty connectors had to be strong enough to pull enormous loads, flexible enough to navigate curves and grade changes, yet accessible enough for rapid connection and disconnection by rail yard workers. Meeting all these requirements simultaneously meant the couplings couldn't be heavily armored without compromising their function. Additionally, the mechanical linkages connecting drive wheels to the locomotive's power plant ran beneath the armored shell where protection was lighter due to ground clearance requirements. Hitting these linkages with concentrated fire might sever the connection between engine and wheels, effectively immobilizing the train even if the locomotive remained structurally intact. A train that couldn't move was a train that became a stationary target for heavier ordnance or had to be abandoned by its crew. James shared his analysis with his flight leader, Captain Thomas Reynolds, a veteran pilot with over 60 combat missions who had a reputation for listening to unconventional tactical proposals. Reynolds studied the diagrams and calculations with interest, asking detailed questions about firing angles, ammunition requirements, and the probability of achieving the necessary hit concentration. His questions were practical rather than dismissive, focusing on execution rather than theory. The tactical challenge was significant. Trains moved, sometimes at considerable speeds. Attacking them required the pilot to execute a diving attack run while calculating lead angles to ensure his rounds intersected the target's future position rather than its current location. The concentration of fire necessary to exploit the vulnerabilities James had identified required holding the firing pass for several seconds while flying directly toward the target, maximizing exposure to defensive fire from the train and surrounding positions. Standard strafing technique called for short bursts from multiple angles, minimizing time in any defensive fire cone while maximizing the area covered by the attack. What James was proposing required exactly the opposite approach: sustain fire from a single optimized angle, accepting increased risk in exchange for concentrated impact at a critical point. The mathematics worked in theory. Whether they would work in practice while flying at 300 miles per hour through a storm of anti-aircraft fire remained to be tested. Captain Reynolds approved a modified mission profile. During the next scheduled armed reconnaissance sweep over the Ruhr Valley, if conditions permitted and a suitable target presented itself, James would be authorized to attempt his proposed attack method. If successful, the technique would be disseminated to other squadrons. If unsuccessful, well, at least they would have tried something different rather than accepting the status quo of ineffective attacks against an increasingly important target set. The mission launched on March 17 at 0630 hours under overcast skies that created a solid ceiling at approximately 8,000 feet. 4 P-47s formed the flight, Captain Reynolds leading, James flying as his wingman, and 2 additional aircraft providing top cover and rear security. The formation departed Belgian airspace heading southeast, maintaining altitude to stay above light anti-aircraft fire while monitoring radio frequencies for intelligence updates on enemy movements. Crossing into German territory brought an immediate change in atmosphere. The ground below showed the devastation of 5 years of war. Bombed cities, cratered roads, destroyed bridges, and abandoned vehicles littered the landscape. But the rail lines remained largely intact, testament to German engineering and the continuous repair efforts that kept supplies moving despite constant air attacks. Intelligence had been correct about increased traffic. Within 30 minutes of crossing the border, the flight observed 3 separate trains moving west to east, likely evacuating equipment or repositioning units. The first 2 trains were dismissed as unsuitable targets. One traveled through heavily wooded terrain that would have made effective attack runs impossible. The second moved through a populated area where missed rounds might have caused civilian casualties. Captain Reynolds maintained strict rules of engagement that prioritized military necessity over target enthusiasm. Patience was rewarded 40 minutes into the patrol when the formation spotted their ideal target. A long military train was moving through relatively open terrain along a rail line that ran through a shallow valley. Reconnaissance had designated this route as a primary supply artery connecting the Ruhr industrial region to forward positions. The train consisted of what appeared to be an armored locomotive pulling approximately 20 cars, many covered with camouflage netting suggesting valuable cargo. More importantly, the surrounding terrain offered clear approach and egress routes with minimal obstacles and few visible defensive positions beyond the train itself. Captain Reynolds called the target over the radio, instructing the flight to orbit at altitude while he and James descended for a closer look. The 2 P-47s dropped from 8,000 feet to 2,000 feet, maintaining sufficient distance to avoid alerting the train's defensive crews while allowing detailed observation. Through binoculars, James could see the armored plates covering the locomotive, the anti-aircraft guns mounted on several flat cars, and the telltale signs of a high-value target that German forces considered worth defending with significant resources. The locomotive design matched the configurations he had studied. The armor protection was extensive but followed predictable patterns. The coupling mechanism connecting the locomotive to the first car was visible, presenting exactly the vulnerability his analysis had predicted. The mechanical linkages beneath the locomotive would be harder to hit due to ground clearance and the angle of attack required, making the coupling the primary aim point for his proposed technique. Captain Reynolds cleared him to execute the attack. The other 2 aircraft would remain at altitude, ready to suppress any defensive positions that opened fire and to provide cover if enemy fighters unexpectedly appeared. James would make his run from west to east, using the morning sun behind him to degrade the effectiveness of the train's anti-aircraft gunners. Captain Reynolds would follow 30 seconds later, attacking from a different angle to divide the defensive fire and to exploit any damage James might inflict. James climbed back to 6,000 feet and positioned himself approximately 2 miles west of the train. From this altitude, he had potential energy that could be converted to speed during his diving attack, reaching velocities that would minimize his exposure time while maximizing the kinetic energy of his rounds. He rolled inverted and pulled through into a steep dive aimed at a point approximately 200 yards in front of where the locomotive would be when he reached firing range. The P-47 accelerated rapidly, air screaming past the canopy as the altimeter unwound. At 3,000 feet, he rolled wings level and began tracking the locomotive through his gun sight. The train was moving at perhaps 30 miles per hour, requiring substantial lead to ensure his rounds would impact the coupling rather than the space it had already vacated. His engineering training allowed him to calculate the necessary deflection almost instinctively, adjusting his aim point to account for both his aircraft's velocity and the target's movement. At 1,200 feet and closing at over 350 miles per hour, he pressed the firing trigger. 850 caliber machine guns erupted simultaneously, their combined roar audible even over the engine noise. The recoil was noticeable despite the P-47's substantial mass. Tracer rounds drew brilliant lines through the morning air, converging on the space between locomotive and first car. He held the trigger down, maintaining precise aim despite the buffeting and the instinctive urge to break off the attack as defensive fire began reaching toward him. Seconds stretched into seeming hours as his rounds hammered into the target. He could see metal fragments exploding from the impact point, bright flashes indicating strikes on steel. The coupling mechanism was being subjected to forces it was never designed to withstand. Dozens of armor-piercing rounds striking within a concentrated area, each impact adding stress to metal already weakened by previous hits. Something had to give. The coupling shattered at precisely the moment James reached minimum safe altitude. The massive steel connector that had been designed to pull hundreds of tons simply disintegrated under the concentrated barrage. Metal fragments spun away in all directions as the connection between locomotive and train severed completely. He pulled hard on the stick, hauling the P-47 into a climbing turn that subjected his body to crushing G-forces while his vision narrowed to a tunnel of graying consciousness. Behind him, the locomotive continued forward for perhaps 50 yards before the engineer realized something catastrophic had occurred. The train cars, suddenly released from their pulling force, began to slow and bunch together as momentum carried them forward into each other. The accordion effect rippled down the entire length of the train as each car collided with the one ahead, creating a chain reaction of impacts that derailed several cars and sent cargo spilling across the tracks and surrounding terrain. Captain Reynolds made his pass 30 seconds later, his guns tearing into the now stationary locomotive. Without the coupling to target, he concentrated fire on the mechanical linkages James had identified as secondary vulnerabilities. His rounds chewed through the protective housing and severed critical connections between the engine and drive wheels. Even if German engineers managed to repair the coupling, the locomotive itself was now mechanically dead, incapable of generating the power needed to move such a heavy load. The defensive anti-aircraft fire that had been sporadic during the initial attack intensified as the train crews realized they were under sustained assault. Tracers filled the air, creating deadly patterns that the P-47s had to navigate while making their attacks. The two aircraft providing top cover dove into the fight, suppressing the anti-aircraft positions with strafing runs that killed gun crews and destroyed several of the flat car-mounted weapons. The entire engagement lasted less than 4 minutes from first shot to final withdrawal, but in that brief span, the flight had accomplished what previous missions had failed to achieve. They had not just damaged a German train. They had developed a replicable technique for destroying armored locomotives using weapons and tactics available to every fighter squadron and theater. As the four aircraft climbed away from the target area and turned west toward friendly territory, James keyed his radio microphone to provide a quick damage assessment. The locomotive was immobilized. Multiple cars were derailed. Secondary explosions suggested ammunition or fuel storage had been compromised. Most critically, the technique had worked exactly as predicted. Concentrated fire at the coupling mechanism had achieved catastrophic results that dispersed fire across the entire target never could have accomplished. The flight returned to base without incident, landing at a 78 just after 0900 hours. Ground crews immediately began rearming and refueling the aircraft while pilots headed to debriefing. Captain Reynolds filed a detailed after-action report describing the new attack method, including specific aim points, recommended firing angles, and ammunition expenditure estimates. Intelligence officers reviewed gun camera footage that had captured the entire engagement, confirming the coupling destruction and subsequent train disablement. Within 24 hours, the technique was being disseminated to other fighter squadrons across the 9th Air Force. Within 72 hours, pilots across multiple commands were receiving briefings on the specific vulnerabilities of German armored trains and the methods for exploiting them. What James had discovered through analysis and confirmed through combat was rapidly becoming standard tactical doctrine. The impact on German logistics was immediate and devastating. As word spread that American fighters had developed effective methods for destroying armored trains, German rail traffic patterns changed dramatically. Trains that had previously moved during daylight hours now traveled only at night. Routes that had been used regularly were abandoned in favor of more circuitous paths that offered better concealment. The speed of rail movements decreased as engineers became more cautious, watching the skies constantly for the distinctive silhouette of approaching P-47s. But these defensive adaptations only worsened the situation for German forces. Slower trains meant fewer supplies reaching the front. Nighttime movements meant reduced efficiency and increased accidents. Circuitous routes consumed more fuel and subjected rolling stock to additional wear. The cumulative effect was a logistics system that became progressively less capable of supporting military operations precisely when German forces needed maximum supply throughput to counter Allied offensives. James flew 17 more missions before the war in Europe ended in May 1945. On 6 of those missions, he encountered and engaged armored trains using the technique he had pioneered. All 6 attacks resulted in destroyed or disabled locomotives. Other pilots in his squadron achieved similar results. Across the entire tactical air force, the success rate against armored trains climbed from less than 20% using conventional methods to over 70% using the concentrated fire technique. The broader implications extended beyond simple target destruction statistics. German forces attempting to evacuate equipment, reposition units, or bring up reinforcements found their rail network increasingly unreliable. Trains that did reach their destinations arrived days behind schedule. Cargo that should have been delivered intact arrived damaged or destroyed. The psychological impact on German logistics personnel was profound as they watched a transportation system that had functioned effectively for years gradually collapse under sustained air assault. Intelligence reports captured after the war revealed that German high command had recognized the severity of the rail interdiction problem but lacked effective countermeasures. Adding more armor to locomotives made them too heavy and reduced their operational efficiency. Increasing anti-aircraft defenses on trains diverted weapons needed elsewhere and still proved inadequate against determined attacks. Attempting to disperse critical supplies across multiple trains simply created more targets for Allied fighters to engage. James received a Distinguished Flying Cross for the original mission that had demonstrated the technique's effectiveness. The citation specifically noted his analytical approach to identifying tactical vulnerabilities and his willingness to test unconventional methods when standard procedures proved inadequate. But he understood that the real significance wasn't personal recognition but the systematic application of engineering principles to combat problems. After returning to the United States in late 1945, he spent several months working with Army Air Force's Tactical Center personnel to document the lessons learned from the train interdiction campaign. His technical background allowed him to explain not just what had worked but why it had worked, providing insights that informed post-war doctrine development. The principle of concentrated fire at specific vulnerable points rather than dispersed fire across general target areas became a cornerstone of ground attack training. Years later, when military historians examined the air campaign over Europe, they identified rail interdiction as one of the most effective applications of tactical air power during the war. The destruction of German logistics infrastructure contributed directly to the collapse of organized resistance by preventing the movement of supplies, reinforcements, and equipment necessary for sustained military operations. Within that broader campaign, the development of effective techniques against armored trains represented a critical breakthrough that transformed a frustrating target set into a lucrative opportunity. James rarely spoke about his wartime experiences after returning to civilian life. He completed his engineering degree and spent 4 decades working in industrial design, applying the same analytical approach that had served him in combat to solving manufacturing and production challenges. But colleagues who knew his background occasionally asked about specific missions or tactical decisions. His responses focused less on the drama of aerial combat and more on the problem-solving process that had allowed him to identify vulnerabilities others had missed. The lesson he drew from that March morning over the Ruhr Valley wasn't about courage or skill, though both were necessary. It was about the power of systematic analysis applied to seemingly intractable problems. German engineers had designed armored trains to be invulnerable to air attack using the weapons and tactics then in common use. They had succeeded in creating formidable targets that resisted conventional attacks. But every defensive system has vulnerabilities. Every piece of armor has weak points. Every mechanical system has failure modes that can be exploited if properly understood. The key was refusing to accept that a problem was unsolvable simply because initial attempts had failed. It required looking beyond surface appearances to understand underlying principles. It demanded willingness to test unconventional approaches even when conventional wisdom suggested they would fail. Most importantly, it needed the courage to act on analytical conclusions even when doing so meant flying directly into concentrated defensive fire with only mathematical calculations as reassurance. The trains that burned across Germany in spring 1945 represented more than tactical victories or destroyed equipment. They symbolized the broader application of American industrial thinking to military problems. German forces had relied on engineering excellence and technical sophistication to create defensive advantages. American forces responded not by matching that sophistication but by applying systematic analysis, operational flexibility, and overwhelming resources to exploit whatever vulnerabilities existed. James understood that his contribution had been relatively small in the vast scope of the war. Millions had served. Thousands had made discoveries or innovations that contributed to victory. But he also recognized that wars were won through the accumulation of such contributions, each building on previous efforts until overwhelming advantages emerged from countless individual actions. The armored trains he had helped destroy represented just one small part of a logistics network that sustained German military power. But destroying that one part created cascading effects that weakened everything connected to it. The strategic lesson transcended the specific tactical situation. It spoke to the fundamental nature of modern warfare, where victory often depended less on battlefield heroics and more on the systematic destruction of an enemy's ability to sustain military operations. Cutting supply lines proved more decisive than winning pitched battles. Preventing reinforcements from arriving mattered more than destroying forces already engaged. Creating logistical chaos in rear areas contributed as much to victory as direct combat on front lines. In the end, the story of those train attacks wasn't really about flying or shooting or tactical innovation, though all played roles. It was about the power of human intelligence applied systematically to practical problems. It was about refusing to accept limitations imposed by others and instead seeking solutions through careful analysis and courageous action. It was about understanding that seemingly invulnerable targets always possessed weaknesses that could be exploited by those willing to look carefully enough and act boldly enough when opportunities appeared. The coupling mechanisms that shattered under concentrated machine gun fire represented more than failed engineering. They symbolized the inevitable vulnerability of any system, no matter how carefully designed, when subjected to attacks it wasn't specifically designed to resist. The lesson applied far beyond military tactics to encompass broader truths about problem-solving, innovation, and the human capacity to overcome obstacles through intelligence and determination. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.